Next problem is called find smallest letter greater than the target. We are given an array of characters called letters that's sorted in non-decreasing order and a character target. There are at least two different characters in the letters, and we have to return the smallest character in the letter that is lexicographically greater than the target. If such character does not exist, we have to return the first character in letters. So for example, here we have target A, and the first letter that's larger than the target is the letter C, and it's the smallest, lexicographically smallest letter in the input array. So we just return the letter C. Next, for the letter C, we are checking basically the first element, and it's the same one. So we have to move forward in the array because we know it's non-decreasing. So it either will have a duplicate or a larger letter. And in this case, we will have F, which is larger than C, and it's the first smallest letter, then it's larger than the C. So we just return it. In the last example, we have target Z, and we know that there's no letter that's larger whatsoever than Z. So we will just return basically the first element, whatever the element is. In this case, it's X, so we just return it as the our function output. The constraints are the following. The letters input array size is ranging from 2 to 10 to the 4th. All letters inside the letters input array are lowercase English letters. They are sorted, as we said, in a non-decreasing order, and the letters contain at least two different characters. And one important note, the target is also a lowercase English letter. So to solve this, we first know the nature of the array because we are searching and the array is in a non-decreasing order. A natural choice is to try binary search for this problem. But we will there will be some modifications to the regular binary search to make it work for this problem. First thing to note is that we are not searching for the exact target. We are searching for the closest one that's greater than the target. And whenever we have this closest and not the exact, I use the following boundaries. I use the low. I set it to the start of the array of the exploration space, and for the end boundary, I put the basically the length of the input array. So it's basically the high boundary is pointing out of the array, and that reflects our invariant. Instead of having low equal smaller or equal to high, we have to make the invariant that low is always smaller than the high, because we will be checking the elements at specific indices, and if we have low is equal to high, we might be out of boundary. Next, we will do the calculation for the mid, and we will check if the current element at the mid is larger than the target. And if it is, we don't just skip the whole right half. We skip almost the whole right half, but we except for the element at the index mid. Why do we keep the index mid? Because we know it's it's currently the lowest possible letter that is higher than our target. So it might be the best candidate that we have. So we have to keep our high at the mid. We have to set it at the mid index. But if we find at the index mid is smaller, then basically all the elements before are smaller than our current target, so we can skip the whole left side. And if we are done with our traversal and we didn't find the element that is larger than our target, the low and high will be pointing to the same element. That element will be out of boundary. It will be the initial value of the high, and because it's out of boundary, we know that we haven't found the element that's larger than the target. And because we know that, we will just do modulo of low, and in a case where low is equal to high and they're pointing to the first element inside the boundaries of the input array that's larger than the target, then we will have a valid index, and we will just return that letter. But if low and high are pointing to the out of boundary, they will be pointing to the index that's equal to the letter's input array length. So when we apply modulo, that will basically revert back to the 0, and we will just return the first element because the index 0 corresponds to the first element. And because we are using the binary search, the time complexity is logarithmic in this case, and for space complexity, we are not creating any additional data structure, so we have a constant space complexity.